In this video, we'll explore how the theories attempt to describe the universe, but fail to explain the smallest scales of existence. We'll examine groundbreaking concepts like space-time, black holes, and the holographic principle, questioning whether space and time are fundamental or simply illusions. Join us as we dive into the mysteries of physics and seek clues toward a quantum theory of gravity. The Planck length physics' greatest puzzle. The Planck length, trillions of times smaller than an atom, poses one of physics' most complex challenges. As we attempt to understand what happens on such a tiny scale, around 10 to the minus 33 centimeters, the usual laws of nature fail us. In this realm, where the fabric of space and time seems to unravel, the order of physics dissolves into chaos. Despite decades of research, we've reached a troubling conclusion. Our best theories, quantum mechanics and general relativity, cannot fully explain this level of reality. To delve deeper, we must push for new physics. This video will guide us through building the stage of space-time from the ground up, only to dismantle it again in pursuit of a quantum theory of gravity. Along the way, we'll confront some fundamental questions. Is space-time real, or could it be an illusion at the quantum level? Do concepts like where and when have any true meaning in the deepest layers of reality? In 1637, mathematician René Descartes envisioned a hidden mathematical framework for space, laying out the Cartesian grid with x, y, and z coordinates. This grid became a backdrop for understanding reality. A few decades later, Isaac Newton added time as an independent, rigid element of the stage. However, space and time were considered separate until 1905, when Albert Einstein's theory of special relativity challenged this view. He revealed that time is relative depending on an observer's movement in space. This discovery hinted that space and time are interconnected, forming a four-dimensional entity called space-time, with three spatial dimensions and one of time. Einstein's curved space-time and the birth of general relativity. Einstein began to wonder about the shape of this unified space-time. He visualized space-time as a manifold, a collection of grids connected to form a surface that can curve or bend. Locally, the manifold looks flat, but on a larger scale, it bends in response to matter and energy. This curvature explains gravity, the bending of space-time caused by mass. To measure this bending, we need a ruler to account for stretching and warping. In flat space, we calculate distances using a simple equation based on Pythagoras' theorem, but on a curved manifold, we need a modified ruler, called a metric. Einstein extended this concept, creating a metric to describe how space-time curves in a four-dimensional universe like ours. The amount of bending is determined by the presence and amount of matter and energy, and this relationship is the heart of Einstein's field equation, the crowning achievement of general relativity. Quantum mechanics meets general relativity and breaks down. Einstein's theory, elegant as it is, breaks down at certain points, singularities such as the Big Bang and the centers of black holes where matter and space-time curve infinitely. These infinities signal that the theory cannot describe physics at such extremes. Furthermore, at subatomic scales, where quantum mechanics governs, particles are too light to curve space-time noticeably. Quantum mechanics, unlike general relativity, describes reality probabilistically, with particles existing in overlapping amplitudes rather than fixed positions. The quantum puzzle space-time needs quantum gravity. To unify these two theories, we need a quantum theory of gravity, one that treats space-time itself as probabilistic. Yet, as we probe closer to the Planck length, even the concepts of here and there start to blur. If we try to measure distances below this length, our ruler dissolves into quantum uncertainty. Experimental physics has limits. Even the most powerful particle accelerators fall short of probing the Planck scale. A collider large enough would be the size of the Milky Way and would collapse into a black hole. Thus it seems that space-time below the Planck length lacks physical meaning. The holographic principle, a new frontier. In the 1970s, researchers Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, proportional to their surface area, not their volume. This surprising finding led to the holographic principle, which suggests that everything within a black hole could be encoded on its surface. This idea evolved further, proposing that our entire universe could be a holographic projection from a lower dimensional surface. Space-time as an emergent property. The holographic principle hints that space-time might not be fundamental, but rather an emergent property created by quantum entanglement, the interconnectedness of particles on a fundamental level. When particles are entangled, they become inseparably linked. This may mean that entanglement is what creates space-time. In certain theoretical models, such as the ADS-CFT duality, the math of space-time geometry corresponds directly to the math of quantum systems in a lower dimension, suggesting that space-time itself is knit together by entanglement. What lies beyond? The search for a quantum theory of gravity. Despite significant advances, the holographic model doesn't perfectly fit our universe's geometry, and more work is needed to find a theory that describes our universe. Testing the holographic principle remains a significant challenge. As we push beyond our current limits, scientists are left to ponder. If space-time and gravity emerge from more fundamental processes, what truly defines reality? The future of physics beyond space and time. Space and time are foundational to science and to how we experience reality. If they are emergent properties rather than fundamental, we must rethink these concepts and discover what lies beneath. This quest for understanding the very nature of reality stands as one of science's most profound challenges.